people who are following me here on good old YouTube channel. You may have noticed I've been kind of out of commission for a little while here. It's been a while since I've created a video. Many of you know I started with my 5th grade videos, and I'm teaching 6th grade this year. So I'm going to do review 6th grade videos. I want you to know that this assessment here that I'm doing, it's kind of based on my district's kind of assessment, and so it doesn't really cover any particular math program per se, although a lot of it's based on the Go Math, 6th grade. But it's the standard that we're looking at. First thing is oh really? Okay, we got ourselves here a math whiz. Something that you may not know. I used to use a smart software, and I recently upgraded my computer, and I no longer use that free version of Smart, which is really cool. Now they want lots of money. Well, you know how it is. So anyways, I am teaching using the Active Inspire software from the Promethean board. So we have ourselves a little visitor here. She appears to be a math whiz there. Although, come on, she's using a calculator. I know, look at that. Looks like she's got herself a parabola there on her little scientific calculator. So you're a math whiz, eh? Okay. Nice to have you aboard. So our objective here today is to review the Common Core State Standard, 6th grade, for the expressions and equations math standard, which states write and evaluate numerical expressions involving whole number exponents. Okay, so this is our focus today. It's time to go ahead and get started here, and let's turn to the next page here. First one says consider the following power. I see 3 raised to the 3rd power. Sometimes we say the 3rd power of 3. I guess there's different ways that you could say that. I always tend to say that as 3 raised to the 3rd power. Here you could say 3 cubed because 3 is cubed. I do have some little frames here I need to fill in. It says the base is blank and the exponent is blank. Well, I'm assuming they're referring to what the base is. So something that we can point out, first of all, the base holds that exponent up. So our 3 is the base. It just so happens that our exponent, which you see is in blue, that is also a 3. So in this case, I guess I just say that the base is going to be 3. And then, of course, our exponent is going to be 3. So keeping in mind, there is the base. Ding, ding, ding. Yes, and there is the exponent. Okay, cool. That says one way to read the power is to say, well, I think I already told you I would state it 3 raised to the 3rd power. You could also say 3 to the power of 3. I mean, that's another way you could say that. There's not one right answer here. I think that there's just different ways. Like I said, you could also say 3 would probably be the quickest way if you wrote it. 3 cubed. And you could use that because you have a 3. And 3 is cubed because it has 3 dimensions, right? Write the power as an expression. Well, 3 raised to the 3rd power is the same thing as saying 3 times 3 times 3, because that's what the exponent tells us. It tells us that the base is going to multiply itself 3 times. It does not mean 3 times 3. That's a very common pitfall with, well, I was going to say 5th graders because this standard actually used to be 5th grade many, many years ago. But now the Common Core has moved this particular standard up to 6th grade. However, many students would make the mistake to put 3 times 3 and their answer would be 9. It doesn't mean that. It means 3 times 3 times 3. You're taking the base and you're multiplying it 3 times. Okay? I hope that makes some sense. So find the value of the power. Well, now if we have 3 times 3 times 3, you can see that our 3 times 3 gives us 9, right? And then 9 times 3, 27. So 3 cubed then means 27. Cool, all right. Time to move on. Okay, now this next problem here, number 2, it says, Mr. Wara, hey, that's me, made the following observation. Okay, I don't know if I made this. Let me see. It says, when I compare 2 numbers with exponents, the number with the larger exponent will always have a greater value. I don't remember making that observation, but let's just go along with the program. Okay, so if you're looking at 2 exponents, the number with a larger exponent will always have a greater value. When they use the word always, well, let me see, what do I have to do down here? It says provide an example showing why Mr. Wara's observation is correct. But it also says provide an example showing why Mr. Wara's observation is incorrect. Assuming by these 2 squares, I'm going to deduce, that's right, that you could probably make an example where that's true and an example where that's not true. Let me see. Well, we could do the one that we just had. We had 3. Remember, that was raised to the third power. And we could kind of compare that with 3 raised to the fourth power. My observation was the one with the larger exponent will always have a greater value. Well, in this case, we already know that that's 27. So in this case, 3 is being multiplied by one more power, okay, of 3, if you will. 3 times 3 times 3 times 3. Here we have 9 times 9 then, because 3 times 3 is 9. So we're going to have 81. So yeah, when I compare these two, definitely 81 is greater than 27. So that's true. So I could say that 3 raised to the fourth power, okay, is greater than 3 raised to the third power. Now it says provide an example showing why Mr. Waras' observation is incorrect. Okay, so now I have to find an example where that's not true. Well, I know one thing that happens when we learned this when we were multiplying fractions. When we multiplied fractions, what happened was is we would end up with a product that was less than the factors being multiplied. For example, I think that we could do this here. What if we just said, okay, I'm going to show, let's take 1/2 raised to the third power versus 1/2 raised to, well, let's have some fun. Let's make it the fifth power. Now, clearly, this particular base here, and this is a number, it didn't say that it had to be a whole number. It just said when I compare two numbers, and 1/2 is a number. So 1/2 raised to the fifth power. So that would work. Well, think about that. This is 1/2 then, times 1/2 times 1/2. Remember, it's not the 3 times 1/2. Well, if you remember from multiplication of fractions, 1/2 times 1/2 times 1/2 is just, I'm going to multiply the numerator, which is just 1, and then I'm just going to multiply the denominators, which is 2 times 2 times 2, which we know is 8. So we end up with a product of 1/8. Okay, let's look at the other one here. We're going to take our 1/2 times our 1/2, and you can start to see what's going to happen here. I'm trying to make this all fit in here. Oh boy, talk about squeeze play. Well, we're going to have the same thing. 1 is going to be the numerators multiplied. Now you have 2 times 2 times 2 times. So it's going to take a little bit more. So remember, don't try to add them. Okay, that's not a good thing. Okay, we don't want to add this and say 2, 4, 6, 8, 10. That's not what that is. It's 2 times 2, which is 4, 4 times 2, which is 8, 8 times 2, which is 16, and 16 times 2, which is 32. Now, when you look at these two, you can see what happened. If you recall, yeah, if you have unit fractions, and a unit fraction is a fraction that has a numerator of 1, these are unit fractions, then we can look at the denominator and compare them. And 8 is clearly smaller than the number 32 if they were whole numbers. But as denominators, no, eighth sizes are larger than 1/32. Okay, and I've always tried to explain, when you go to the pizza parlor, kids love pizza, and you look at the pizza, and if it's divided into 8 pieces, you know how big it's going to be. But if you divided that same pizza into 32, you'd end up with some pretty small slices. Okay, therefore that makes that number smaller. And look, it had the larger exponent. So in this case, no, 1/8 is greater than 1/32. All right, down below it says, is Mr. Waras' observation correct or incorrect? Well, I'm going to say my observation. Wait a second, that's me. Yes, my own observation. Mr. Waras, you are incorrect. I challenge you. Yes, because it's not correct. It's incorrect. And it's incorrect because of really, when I look at it, I look at one word. That one word up here is always. It said when I compare two numbers with exponents, the number with the larger exponent will always have a greater value. And that's just not true. So I'm going to say no. Mr. Waras' observation is incorrect. Now it does say explain using your examples. Well, I think I already explained using my examples. I explained that when I took a fraction and raised it to different powers, one to the power of 3, one to the power of 5, that changed the product. And in fact, when I multiplied a fraction, and I showed you the example here, 1/2 raised to the fifth power, you end up with a smaller product. So in that case, even though the number was raised to a higher power, I ended up with an answer, a product that was less than the one raised to the third power. So no, Mr. Waras' observation is incorrect because it would depend on what number, and when I say what number, I'm thinking of a value of the number, okay? And I'm going to use my little pound sign as an abbreviation for number. So it would depend on what number is used as the base. Okay, that would make a big difference right there. And I'm trying to think what other number, unless you use like the number one raised to the fifth power is just going to be one. Two raised to the third power is going to be greater, even though, so the identity property with one would maybe change that as well. Otherwise, I can't think of any other examples other than fractions where this might be true. Anyway, so I corrected my own mistake, my own observation. Woohoo! Yeah. Okay. All right. Hey, that's great. You're that little math wizard there. Again, I don't have the heart to tell her that you know you're using a calculator. Yes, okay, that's cool. All right. Yeah, maybe we'll let you teach a lesson here at some point. Oh my goodness. You do have a lot of freckles, don't you? Can I add to your freckles? Wee, yeah. Very cool. I like them. I know. Mr. Warren, leave her alone. I know. Okay, sorry. Anyways, number 3 says write an expression that is equivalent to 64 using each of the following numbers and symbols once in the expression. It does say you have to use all the symbols once in the expression, so at least that's helpful. It means I have to use every one of these and to get 64. Well, that means I'm going to have to use this parentheses at some point. Probably the best way to show that, I don't know. Let me see here. So if we just took, we don't have any time symbol. Notice that there's no times. So I have this 2, 4. So something needs to be added. Here's my addition sign. You know, all you can do is really try some different combinations. If I were to say, well, what if I took 2, plus 4? I'm just going in order here. And then I have a divided sign I have to use here at some point. I don't know, divided by. I have another 2 yet, raised to third power divided by 2, maybe raised to the power of 3. Now I've used my parentheses, division, add. Did I use all the numbers? I did. So I can see what I get. And it looks like here I'm going to have to do the exponents first. So let me go ahead and do that. So 2 plus 4 divided by, we know 2 raised to the third power. That is 8. So that's going to equal that. Now I have to do my division. So I have to do 2 plus, and 4 divided by 8, well, that's just 1/2. So you can see how off I am here. So my answer would be 2 1/2. Okay, so that's not working, is it? Not at all. Time to get the old eraser. Goodbye. All right. Now, normally I would tell you keep that kind of stuff on your paper. So since our number was so low, it's like we need a really large number. So maybe I just need to kind of change this up a little bit. If we went a different way, if we said 4 divided by 2, that would be 2. Oh, this would work. 4 divided by 2 equals 2 plus my 2 would equal 4. 4 divided by 2 is 2. 2 plus 2 is 4. We get to raise that to the third power. So could I put my parentheses here and then raise it to the third power? I'm just trying these different combinations to get that answer. Now 4 divided by 2. So we have to do what's in parentheses first. So 4 divided by 2 is 2 plus 2. There we go. Aha. And then 4 raised to the third power. Oh, I love how it all works out. Okay, I think to create this is good because it got me to think about the different combinations. I guess that's the key. Anyway, oh, I see you knew the right answer all along. Sure, you were trying to shout out at me, letting me know. Okay, here we go again. It's all about those little caricatures again. Yes, before it was animals and now it's like this little person here. Oh, Susie. Her name is Susie. Why does that name sound familiar? Susie. Sure, you look like a Susie. Okay, let's go on to the next problem. Okay, number 4. It says, select all of the expressions that are equal to the expression 3 to the power of 4 plus 9. Okay, now the first one is I'm going to come over here and I'm just going to write these out because I like to be able to show my work. So 10 raised to the second power minus 10. 10 squared is 100, right? Because that's 10 times 10 minus 10, in this case, is 90. Okay, now what we're going to do is we need to check to see is that expression the same as that expression up here. Well, 3 raised to the fourth power, we did this one earlier. Remember, 3 raised to the third power was 27, so one more power was 81. Remember, 3 times 3 times 3 times 3. So that's 9 times 9. So that's going to be 81. And then we have plus 9, 81 plus 9. Look at that. Yoo-hoo! Yeah. That's right. That's at 90. So you know what? This one is definitely has the same value. You get a little star. Yeah. Okay. And then B says 3 raised to the third power plus 9. Well, 3 times 3 times 3. We figured that one out. 3 times 3 times 3 was equal to 27. 27 plus 9? No, not going to happen. I get 36. So, sorry, B, you are not in the winner circle. Anyway, we come to C. C says 3 squared plus 5 squared. All right, I think I need a little bit more room here. So 3 squared is just 3 times 3, which is 9. And then 5 squared is just 5 times 5, which is 25. Whew. Again, look at we end up with 34. Nope, sorry. Now D, we have 4 raised to the third power. I thought we had that earlier. 4 times 4 times 4. Remember that one? That was 64. I remember that one. Plus 6 squared, which is just 6 times 6, which is 36. Aha. We ended up with 64 and 36. It looks really good here. 10. Oh, no. We end up with 100. Close, but no. That does not meet. And the answer that we're actually looking for is 90. A is the correct answer. You win. Okay, cool. Now let's go on to the next problem. Question 5 says use a factor tree to find the prime factorization of 48. Oh, I love doing this. I love factoring numbers because, well, first of all, factor just in the word lets you know that something, right, times something, in this case I'm using that symbol, is equal to a product. So when you're finding prime factorization, it's like they're giving us the product of 48. So we just need to find two factors of 48. Well, that's easy enough. Here you can choose any two you want. I happen to like 12 times 4 because I happen to know that 12 times 4 is equal to 48. But there's a lot of possibilities. Now what you do with the prime factorization when we're doing the factor tree is we're factoring all of the numbers into what we call prime numbers. And remember, prime numbers, this is just a review, prime numbers are those numbers that have exactly, woo, oh, kind of sloppy there, exactly two factors. They have to have exactly two factors. So over here, that's not true because 4 has more than two factors because 4 has 1 times 4 and then 2 times 2. So this actually has 3 factors. So what we do then, if it has more than 2 factors, is we continue on. So we end up with 2 times 2. Cool. So with 2 times 2, well, 2 is a prime number because 2 only has 1 times 2. So 2 is a prime number. So since 2 is a prime number, I like to circle it because if this is a factor tree, then these could be like the flowers, you know what I mean? The blossoms. Yeah, pretty cool. Okay, so I'm done with that. Now I come over to the 12, and that's not a prime number because I can do 3 times 4, for example. Now 3, 1 times 3 is a prime number, 4 is not. So I can go ahead and put a flower with a 3. See now, that's a prime number. 4, we already know we need to do 2 times 2. So let's go ahead and do that. 2 times 2. And of course, that means we have 2 more prime numbers. So all the flowers are your prime numbers. So since a prime factorization of 48 then would have to be 2 times 2 times 2 times 2 times 3. Wow. Okay, those are all, that's what we say is prime factorization. That seems pretty clear, right? Now that can also be written as 2 raised to the 4th power because we have that base 4 times 3. We tend to write it this way. Okay, that was a lot of fun. Okay, my friends, boy, I tell you, that's the end of this video. Woohoo! Yeah. Oh my goodness, a little 6th grade review. It seems kind of weird doing these problems because years ago, this used to be a 5th grade standard. So it's almost like getting a second chance to get this and learn it in 6th grade. I hope you found it easy enough. Hey, feel free to send me a comment, a question you have about my video. Hey, if you're not a sub, why don't you join the growing team, my friends? Now, like I always say, live long and prosper, my friends.